All right, everybody, so this is our second video on integration by parts. And we'll call it integration by parts continued, 7.2b. And I want to show you a couple of things. Sometimes you have to use integration by parts twice. You may have already figured that out. And sometimes you have a definite integral, right? So we have actual numbers to plug in this time, which is just extra work. So I don't always give that to you right off the bat. So this is day 2. Hopefully we're going to be able to go a little bit faster, a little bit cleaner with this thing. So let's just give it a shot. I personally always like to set up the box with everything in it. So I like to have this to reference. So I'll just do u and du, and then I'll do another one for dv and v. Now if you don't like that order, that's fine. I just like to put my two things on top that are coming from my integral. So my u is going to simply be, well, Lippitt says choose logarithms, and there's none. Then it says choose inverse trig. We're not really dealing with that generally. It's possible you'll have to do something like that, but for most of my calculus classes, we're not going to have time. P is polynomial, and polynomial is x squared. Okay, even though that's a fancy word for it, polynomial is just x squared. So I'm going to make u x squared, or whatever else it would have been, and that's going to be 2x dx. Make sure your du has a dx in it. Make sure your dv has a dx in it if that's the variable we're working with. So dv would be e to the x dx, and if I integrate e to the x, I just get e to the x. So I'm going to do uv minus v du. So this actually equals uv minus the integral of v du, uv minus the integral of v du. So du is this, 2x dx. Okay, so that's where we're at. So we haven't gotten, we still have a product. You know what I'm saying? Like, we're not really taught how to integrate products unless we have a chain rule. So we're in a bit of a situation. We don't like that there's a product here, so I'm just going to simplify a little bit and see if we can maybe do this again. Now, if you're careful, if you really go down far and you don't like look at your previous substitutions, you could probably reuse if you're doing integration by parts twice. That's what's going to happen here. So I'm going to scroll down so that you can't see what happened up there, right? Scroll that down, and I'm going to get rid of this too. Bear with me, my apologies. Okay. And what's going to happen is we're just going to do the whole process over again. So we can still use u and dv and all that stuff if we want in this case, because I've blocked out every memory of it. Maybe we'll use a different color this time. So u du. So u in this case, we need to work on this guy. So u is x, du is dx. That's dv. And we know that v would be just e to the x. So, well, obviously x squared e to the x doesn't change. The minus 2 doesn't change, right? But now we're working this new problem. So I'm going to put brackets like that. And I'm going to do uv minus the integral of v du, right? v du. I'm kind of going a little out of order, so I don't have to change colors so much. uv minus the integral of v du. That's what I have. Okay, so hopefully that's all seeming okay. We can just do some basics here. I mean, we got x squared e to the x minus 2x e to the x plus 2 integral of e to the x dx. I'm going to not write again. I'm just a little lazy. I know the integral of e to the x dx is e to the x. So I've got that. Good news is everything is in terms of x. So a couple of like little things here. We were doing a definite integral, so we need to evaluate this from 1 to 0, right? So we need to go ahead and evaluate this from 1 to 0. So let's go ahead and do that. So we'll plug in 1, and we'll basically get, let's see, we'll get e minus, I guess, 2e plus 2e. Hopefully that makes sense. That's the first one we plug in. So remember, we're plugging in 1 and we're plugging in 0. Now I'll plug in 0, okay? So remember, we're just doing that regular old fundamental theorem of calculus. 0, 0, and then I think just 2e to the 0. So 0, 0, 2e to the 0. So all that to say, we have e minus 2, I think should be our answer. And that, I believe, is correct. That's the answer that I had written down. So we didn't need to do a plus c, we did an actual definite integral. All right, so lastly, we're going to do this one, which is a special case of repeated integral by parts. And this is probably one of the trickier ones. We look at Lipit, and it says logarithms, we don't have it. Inverse trig, we don't have it. Polynomials, we don't have that. So LIPE, exponentials and trig. So we have to pick either exponential or trig now, which is near the bottom of the list. And we don't love that. So I guess I'll pick exponentials since Lipit says that's the next one to pick. So I'm going to go here. I'm going to assume that we don't need the formula as much. And I will make u the exponential function, which is this. That means du is 3 by the chain rule, e to the 3x, and that's this guy. And then I guess everything else is dv. So dv is cosine of 3x dx. And v is, I think that's going to be 1/3 sine of 3x. Make sure you're comfortable with it. Do a whole integral out if you have to get from dv to v. You should be able to derive v and get dv. So that works for me. So now we do uv minus v du. So let's just go ahead and do that. uv minus the integral of v du, which is 3e to the 3x dx. That was missing. There should be a dx there. uv. So this is 1/3 sine of 3x. So uv minus v du, again the 1/3, we can put it on the outside, sine of 3x. Okay. Okay, getting a little ugly. We're left with this problem here. So this is the problem that we're dealing with. So I'll just bring it down. I'll try to ignore that we already did a u substitution. And maybe I'll simplify in between. So I've got, let's see, 1/3 e to the 3x sine of 3x minus 1/3 the integral of, I think that this 3 and this 1/3 can cancel here. So minus the integral of e to the 3x sine of 3x dx. So that's where we are now. So we can just repeat process and do another u substitution. I just want to make sure I'm on track so far, that I haven't made a mistake, so I don't have to delete all this video. So one moment. Okay, so hopefully you found the error already. I don't want to have to redo everything here, but my mistake, and I think we can fix it pretty quickly, my apologies, is that it was cosine of 2x, unfortunately. So that's a 2, that's a 2, that's a 2. So let's work on that. We got a 2 here, we got a 2 here, we got a 2 here. That means that over here, we have a 2 here, sine of 2x, sine of 2x, and I think even here, right? So it is going to like derail us a little bit. It's not the end of the world, but I think we have 2x here, we have 2x there, and we have a 2 there, okay? So that's where we're at. So provided I haven't made any grave mistakes here other than that one, we should be able to continue on. I'm glad I stopped because it did seem like something was off. So as I'm working through this, I'm just going to do another u substitution. So what I'm going to do is I'll set up my stuff over here. I'll make u equal to, I think again I'll make it equal to the exponential. My dv will be, I think, sine of 2x dx, and my v will be 1/2. The integral of sine is negative cosine, I think. So that's what we want. So let's get to work. So we have 1/2 1/2 e to the 3x sine of 2x minus 3/2, and then whatever this thing gives us, right? Whatever we get for this whole issue. So I'm going to go ahead and do this, just move it down a hair, maybe move this up a hair so we have a little more space. And now what we can do is see what this returns. So this is us applying the formula. So now u v minus the integral of v du. So when I do v du and I'm looking at those and I'm doing some calculations in my head, I'm subtracting the integral of v du. So I think I'm going to have something like this. Okay. That's what I have so far. I'm going to go ahead and simplify this out as best I can. I realize it's pretty messy. It's pretty crazy. And there's a lot of places to make mistakes. So we've got 1/2 e to the 3x sine of 2x minus, or actually plus, I'm going to distribute this. I have 3/4 e to the 3x cosine of 2x, right? And then I'm going to distribute this here, minus 9/4 the integral of e to the 3x cosine of 2x dx. So we're good, but we have this one issue right here, which is this integral. I want you to look at the integral for a second and see if it looks familiar. Does it look like something you've seen before? So we'll scroll back. E to the 3x cosine of 2x. Okay, so spoiler alert, this is it. So what I'm trying to say is this integral right here, right, this original integral, which I'm going to even copy it just to kind of show you, be a little bit more dramatic here, that these are equal. So we know that this integral, right, which is the same as this right here, we could take all of this stuff in the middle, right, all of this stuff, darn, almost got it, and we can group it, and we can shrink it, and we can put it, hopefully we can put it here, right? Let's even do this. Even do this. And I'm trying to just rearrange my thing. And you have it in front of you on paper. You'll probably be able to see it clearly what I'm trying to do here. What I'm trying to say is that these are equal. Okay. So take a second. See what I did. I just showed that that same integral is showing up. This is the original problem equal to whatever we're dealing with right now. And I want to take a second to say that this is what we're trying to find, right? So we're trying to find this. And then over here we have negative 9/4 of this, right? So what I'm going to do is I'm going to add this over. 9/4 of this cosine of 2x e to the 3x. My apologies, not very neat. E to the 3x dx. I'm going to add that over here as well, add 9/4 of this same integral. So like we know that we're adding this integral, right? So we're adding this here, okay? So when we do that, right, what do we end up getting? Well, we get, if you think about it, we get this integral, right? But how many of those integral do we have? Well, we have 9/4 and we have 4/4, right? So we have 13/4. That integral is equal to 1/2 e to the 3x sine of 2x plus 3/4 e to the 3x cosine of 2x. Pretty ugly looking thing. If we multiply by 4/13, we have solved that integral. So if we multiply by 4/13, I'm going to do a little bit in my head. I'm going to have, I think, I'll have 2/13 e to the 3x sine of 2x. And then I'll have here, I'll have 3 over 13 e to the 3x cosine of 2x. And I'm going to pause there and double check that that is our actual answer. And we'll see how that goes. Just give me 1 second. And I just checked our answer, and that is not what we're looking for. But don't worry, I'm just messing with you guys. That's only because we forgot a plus c. Otherwise, this is the antiderivative of this integral right here. So this right here antiderives to that. Okay, sorry, it doesn't look that good. So we should wrap it up there. Definitely took some time. So those kind of problems are a little trickier. They definitely have a lot of computation, but if you think about it in a lot of ways, think about it this way. Cosine, if you do this twice, will go back to itself, right? Or a negative version of itself if you derive it twice. And sine will do the same. So you're kind of in the clear because you're only going to have to do integration by parts twice, and then you should be able to solve out. Yeah, there's a lot of algebra and plenty of places to make mistakes, as you saw. But other than that, it's not too bad. It's very skill-based, right? Repetition, memorization, just computation. So we're gonna stop the video there. Hopefully that went well. I'll see you in the next one. Peace.